brief review of graphing hyperbola. So suppose we have that equation. We know that when we've got a quadratic like this and one of the coefficients is positive, one of them is negative, it's going to be a hyperbola. And we have a standard form that we can put that in where we want to make this equal to 1. So we divide everything by 36, and we get x squared over 9 minus y squared over 4 equals 1. And then we rewrite this as a 3 squared and 2 squared. Now, why would we do that? Well, you could just say it's the standard form, trust me, it works. But there's a very simple reason, which is, what's the simplest thing we could try to figure out about this hyperbola? Let's go ahead and set up graph axes here. It's where are the intercepts of this thing? Well, if I set y equals 0, I'm going to find the x-intercepts. It's going to be where x squared over 3 squared equals 1, or when x squared equals 3 squared, or when x equals plus or minus 3. So that's going to be right here and right here. Very similar thing happens for an ellipse. And that's again why the standard form for ellipse looks very similar to this. Now, for an ellipse, if this were plus, we could find out the y-intercepts here as well. Now, this isn't going to have y-intercepts though, because it says minus a square is a positive number. That's not going to happen. That's okay, because if you're familiar with the kind of thing that the kind of graph that hyperbola has, it only usually intersects 2 of the axes unless it's tilted. We're not going to deal with tilted ones. Okay. So, what's the other thing we want to ask about hyperbola? The crucial thing is the asymptotes. And one rather rough way to think about that is the asymptotes are what happens when x and y get very big. The prediction is that they're supposed to go to some sort of straight line or something like that. Well, why on earth would that happen? Well, if x and y are really, really big, then I've got something really, really big, something really, really big. They differ by 1. Well, this 1 suddenly isn't going to be very significant. If this is like 1,000,000 and this is close to 1,000,000, differing by 1 isn't that different from differing by 0. And so we can make an approximation and get a rough estimate for where the curve is by changing this to 0. So that's a very easy way to remember how to get the asymptotes. You don't have to memorize any formula, you just have to change the 1 to a 0. It's not the same curve, but it's something that's going to be very close to it when x and y are really large. And this, it might not look very different, but it's much easier to solve. Because we can just move the y over, square root both sides, and it's really important that it gets a plus or minus now. And so x is plus or minus 3y over 2. So let's graph those. And I want to observe something that actually makes this process, even though this is pretty streamlined, it actually makes it unnecessary for really sketching it quickly. X is plus or minus 3y over 2. Well, if it's plus, then the slope is 3/2. You know what? Actually, it should have solved for y equals 2 plus or minus 2/3 x. Just wasn't paying attention. There we go. The slope is 2/3, or minus 2/3. And the interesting thing there is that if x is equal to 3, then y is equal to 2. Now that's not a point on the curve, it's a point on the asymptote. Similarly, if this x is minus 3, then y is equal to minus 2. So that line is one of the asymptotes, and then the other one is here. So once I've got those asymptotes, I can sketch it in. Now, let's see. I know it's something that approaches the asymptotes when x and y get big, and it goes through these 2 intercepts. So it can't be the stuff up here or down here. It's got to be this guy. And that's a good enough sketch. Let me show you a real cool, quick way to do that. It's very interesting that when x was equal to 3, notice the 3 here, y on the asymptote was equal to 2. And you can see where that 2 and the 3 came from. Those numbers didn't do anything weird. And so that's one observation, is that it's just plus or minus 3 comma 2, with all the 4 combinations of plus or minuses that form these points that the asymptotes go through. And of course, they go through the origin as well, because there's no shift here. So there's a cool observation about that we can also do, which is, suppose this were a plus. It'd be an ellipse, and the x-intercept would be exactly the same, but the y-intercept would be plus or minus 2. It would be good going through here. So let me put that in color. So there's an ellipse that goes through these guys. Not the world's best ellipse, you get the idea. And there's even another thing. Suppose that instead of the minus being on the y, the minus were on the x. Then they would be y-intercepts, right here and right here. And there wouldn't be x-intercepts. And what would the asymptotes be? Well, if I change this to 0, it doesn't matter whether this is minus plus or plus minus. This calculation is exactly the same and has exactly the same asymptotes. And so there's another hyperbola that has almost the same equation, but just the minus has changed. Oops, that's not very good. Coming in here, these are called conjugate hyperbolas. They're married to each other. If you look up conjugate, where that comes from. And what I usually tell people to do is there's really a box in here. There's kind of a fundamental box that relates all three of these graphs. Whether you're trying to draw the ellipse with plus plus, or either of the two conjugate hyperbolas with minus plus or plus minus, they all have a nice relationship to this box. The one with plus x and minus y is on the right and left sides of the box, and it touches right at the intercepts, right at the vertices. The one with minus x and plus y comes and touches at the top and bottom of the box at the vertices. The diagonals of the box, if you extend them out to infinity, become the asymptotes of the hyperbola, and then the ellipse that's sort of in the same family, that lies exactly inside the box, and it touches it at its four vertices at the intersections of the axes. So, if we wanted to just sketch this hyperbola from scratch, this tells us that with that box, we can basically sketch all three of them all at once very easily. So let's see the most efficient way. Going back to the original example, with this hyperbola, how do you sketch the box? The box is just, the four sides of the box are exactly where the intercepts of the ellipse would have been. And it's just at the 3's and the 2's. 1, 2, 1, 2, 1, 2, 3, 1, 2, 3. You just draw a box, dotted in, that goes between minus 3 and plus 3, and minus 2 and plus 2. These numbers, once you put it in standard form, of course, it's not 4 and 9 or anything like that, but 3 and 2. And then connect the corners. Sketch that in, not very well, and you're done. That's a really nice way to very quickly sketch a hyperbola. And it's then almost trivial to sketch its conjugate and the ellipse if you want to as well. Okay.